Hi, thanks very much, Sarah. Good afternoon to all of you who have joined us today. So I'll take you briefly through the agenda for today's webinar. So I'm going to do a short introduction to Spectrum Centre. Martin is going to kick off with the HF basics, a bit of the theory behind what we're looking at today. Then we'll go straight into the demo, showing you some of the interface in Spectrum E, antenna patterns and how those differ from the kind of standard antenna patterns that we use for transmit receive objects. We'll look at diving into the HF circuit chart generation, look at skywave coverage, ground wave coverage, and then at the end of our session today, we'll have an opportunity for any questions and answers that come about through the presentation. So I'll kick off, share a bit about Spectrum Centre, what we do. So Spectrum Centre, as it says in the slide, is the combined offices of the previous ATDI offices in the US, the UK and Brazil. So we have kind of three main parts to our business. Our first one is the commercial off-the-shelf product, Spectrum E, which is what we'll be showing you today. So all of the features that we'll be showing today are within Spectrum E off the shelf. So Spectrum E is built up of three modules. So we've got a kind of technical analysis used for spectrum engineering, remote measurement, where we're able to connect to remote measurement sensors, and an e-licensing module for allowing license applications to be done online. So we also provide, using the off-the-shelf product, we'll provide enterprise solutions based on modifications to this off-the-shelf solution for generally spectrum regulators, spectrum managers. We'll customize the interface so they can have a customer-facing portal where applications can be submitted, and then the process using the technical analysis module and part of the e-licensing workflows that we offer, those licenses can be completed by the end users. Our final offering is we provide consultancy services. We've got years of experience in spectrum management, technical analysis, and we're able to provide that as solutions for any problems that are challenges that your business is facing. We can work together on those as well. So at this stage, I'll pass you over to Martin, and we can let Martin go through the HF basic slides.
Good morning, good afternoon, good evening, everyone. So before we dive into Spectrum E as a software tool, just going to have a couple brief words about what HF is and what the point of this entire webinar is. So some HF communications basics. So HF, of course, stands for high frequency and is typically referred to as the frequency range between 3 and 30 megahertz. Sometimes slightly lower frequencies in the 2 megahertz range or slightly higher in the low 30 megahertz range. The principles of high frequency communications will still apply to those frequencies, although those bands might have a slightly different name. So HF communications is typically divided into two propagation channels, you can say. The first one is HF skywave. So the way that HF skywave propagation happens is that signals are reflected or refracted off of the Earth's ionosphere. And what the Earth's ionosphere is that's the layer, the electrically charged atmospheric layer, that's roughly 60 to 1,000 kilometers from the Earth's surface. So again, HF skywave propagation is the reflecting or refracting of signals off of this ionized layer. The second way that HF signals typically propagate is through ground wave propagation. And ground wave propagation is especially prevalent at the lower HF frequencies and also in the sub-HF band. And this uses the Earth's surface and some atmospheric layers as a waveguide for signals to travel. Ross, if you can move to the next slide, please. So something that HF is known for is fairly high variability in the ability to communicate at all. And there are several environmental factors that affect the ionosphere, and thus in turn HF skywave propagation characteristics. And now we'll talk about this a little bit more when we're reviewing the software. But a key element to be aware of is that the sunspot number will have a fairly large effect on HF skywave communications. So the sunspot number is the number of these spots on the moon where there are large changes in temperature. Not the moon, sorry, I said sun, where there are large differences in temperature, creating magnetic field variations, and these magnetic field variations actually reach the Earth's ionosphere and change the characteristics of it. So here we can see a chart showing the average monthly sunspot numbers for the past 250 years or so, and you can see it's roughly a 11-year cycle with minima and maximum. So during the maximum times, the average is over 100 sunspots per month. But when we're at a minimum point, there are, sometimes in less than 10 per month. So sunspot numbers have a large effect on HF, but also the month, season of the year, and the time of day. Next slide, please. So with this variation in HF, it's necessary to combat that variability and try to be able to have better quality communications. And another factor in HF is man-made noise, and the man-made noise environments will affect what signal strength is possible to receive and process. So once we get into the technical parameters for the stations that are created in SpectrumE, we will have a look at the man-made noise field and what that means. And something that's used to combat that is called automatic link establishment, or ALE. And this method allows for stations to broadcast a signal on multiple frequencies, ultimately choosing the one with the best performance. Once we have a look at a point-to-point circuit chart, that will make a lot of sense, and as we'll be seeing the variability in signal-to-noise ratio during the course of a day and across throughout the entire HF spectrum. So now I hand off to you, Ross, to start with SpectrumE.
Okay, thanks very much, Martin. So I'll kick off with our introduction to SpectrumE. So I'll initially show you some of the interface features within SpectrumE that are particularly suited to the HF application that we'll be looking at today. So as I log in, we can go straight away to the map, and we can see straight away we've got the world view of the map coming up with our HF network that's placed there as well. So when using HF, the distances that we're talking about when we're operating are sort of thousands of kilometers, or certainly up to thousands of kilometers in distance. So one of the features within SpectrumE that allows us to do that is the ability to have a global view of a map all presented to us, and the ability to scroll around that map without any limitations in terms of that mapping area. So we can go right around the world. There's no limitations in the mapping on the background. So also, when we're looking at the HF, there's other layers that are taken into account within the propagation models that we'll be using today as well. So they're particularly the conductivity layer. So if I load the conductivity layer, we can see again off the shelf we have the conductivity layer for the world, and again we have the ability to scroll around. So what that means, and we have also within the conductivity layer specific one for slightly more detailed for the North America as well. So if we go back to our map, so that's some about the maps and the conductivity interface. And also when we're looking at the HF systems, we're always interested in the distance. So we have our distance tool that will put the crosshair over the site that we're interested in, and then click the distance. and then we can measure the distance and angle from that point to any other point on the map as well. So that gives us an idea when we're measuring sort of coverage ranges or looking at particularly maybe spots or skip zones, as Martin will refer to later. We can identify those as well. So within our HF objects, we're also able to select one of these and look at the object info. So we can put the crosshair over, click the object info, and then click the edit button. So that will take us into the fields and parameters on this one. So we can see the fields here, and what's different about the HF antennas compared to our normal antennas is that over the different frequencies from 3 to 30 megahertz, the antenna patterns change, the frequency response changes with the frequency. So we have a number of antennas from different manufacturers, and again, these can be uploaded using the CSV file format. So if you're able to get the antenna patterns from the manufacturer, we can assist with preparation of that for the correct format to be input into Spectrum E. So we'll see the frequency response. As we move up here, we can see that the response of this antenna changes as we go up the individual frequency. So we can see that the kind of polar response changes in the vertical axis. So and that affects the propagation outputs that we get when they're taken into account by the propagation model that we're using. So that's a brief introduction to the interface and the mapping data and also the antennas. So what I can do now is pass over to Martin to have a look at the Skywave aspects of Spectrum E today. So Martin, are you able to share your screen just now?
1 second. Okay, Ross, can you just confirm that you can see my screen?
Yeah, I can see your screen, Martin.
Okay, very good. So I'm going to continue a little bit here talking about some HF radio parameters, and then we'll have a look at generating and viewing Skywave coverages on the map. And this is just a quick look at the map here. A couple of stations I'd created. There's 6 or 7 here. You can see that they're spread across the entire world, and so we're going to be using, taking to our advantage of the fact that Spectrum has a continually scrolling map, so we can see worldwide coverages. But before we get to that point, I'm going to jump back into the network, grab one of these stations, and we're going to have a look at the parameters just to see what's unique about some of the parameters here. So what we're going to talk about first is the noise environment, or the man-made noise. So high frequency is low enough in frequency that absent, interfering active HF transmitters, that man-made environmental noise is the primary determinant in network performance. So if you're in a particularly noisy area, let's say a city or something like that, or if you're on a particularly noisy craft, so let's say some sort of a ship or an aircraft or a helicopter, your noise environment is going to vary, and then the signal strength of your HF signal has to be a certain level above the level of man-made noise in your environment for you actually to receive, decode the signal, and then that signal to noise ratio is further going to determine the data rate that you can have. So what is necessary in the HF object is to set the man-made noise at the receive location. So in the parameters here for this HF radio, if this HF radio is a receive site, this man-made noise parameter is going to be taken into account. So a fairly common value is negative 150 dB watts per hertz at 3 megahertz, and this is for rural locations, and is set forth by the ITU, and the ITU does have some other values for, you can say, recommendations for man-made noise values. For example, per recommendation 1467, on vessels, on ships, the man-made noise typically is negative 142 dB watts per hertz at 3 megahertz, and so on. So based on this man-made noise, as I mentioned, you need your signal strength has to be somewhat stronger than that man-made noise to actually be received. So that'll determine whether or not you can have reliable communications. So, for example, assuming a 3 kilohertz channel, a minimum signal to noise ratio for a 300 bits per second data rate could be around 5 dB. So now, mind you, we're talking about 300 bits per second, so it's a very slow data rate. Of course, then as the signal to noise ratio increases, typically you'll see increases in the data rate as well. So, for example, 3,000 bits per second should be achievable at roughly 15 dB. But again, that's going to be system dependent. As Ross mentioned, in the HF frequency range from 3 to 30 megahertz, there is fairly wide variation in how the signals behave. So something that's has been invented and is used to combat the variation in signal performance across the frequency range is called ALE, or automatic link establishment. And that is a list of frequencies that is cycled through to establish which one has the best performance. So some ALE networks may have as much as 15 or 20 frequencies. And something that's a little unique about Spectrum E and the HF object is that you can input multiple frequencies at once, and then when you're running your analysis, especially your area coverage analysis, the tool will calculate your coverages for all of these frequencies, and then it'll show you what your signal to noise ratio is achievable using the best frequency out of that range, because the performance varies during the course of the year, and it varies even during the course of the day. So that was a quick look at the HF radio parameters. So now we're going to continue to have a look at some point-to-point charts, or in HF, they're often called circuit charts. So let me grab, for example, Hawaii and let's say Panama, these two stations. And what I'm going to do then is click on the Skywave point-to-point chart function. The point-to-point chart function is going to, well, before it's actually generated, it's going to bring up this month and sunspot number information. So as mentioned during the brief introduction to HF, sunspots are very important to HF propagation. And what Spectrum E has, it has built in information about sunspot numbers. And that sunspot number varies per month. So Spectrum E will show you what month of the year it is. And then when you click on the button with the 3 dots, you'll have 2 options of which sunspot prediction to work with. So those sunspot predictions come from 2 different sources, either the NOAA NGDC, which is the National Geophysical Data Center, and that's run by NOAA, or the Space Weather Services, run by the Bureau of Meteorology of the Australian government. So based on which predicted sunspot number you want to work with, you can choose that one. So let's say we want to go with IPS in that case, and IPS is predicting a very low sunspot number of 1.8. So I'm going to click on chart now to generate that point-to-point circuit chart. So in this point-to-point circuit chart, several things to point out. This text at the top will show you information about your transmitting station, about your receiving station, the month you're running it for, the sunspot number, the distance between the 2 stations, and their azimuth. So now there's a bunch of numbers going on, and we have an X and Y axis. So your x-axis represents the 24 hours of the day, and your y-axis represents your frequency, so from 0 to 30 megahertz. On the right-hand side, that colorful bar chart tells you what your signal-to-noise ratio is. And then within the chart itself, there are areas that are filled in color, and there are two lines. So the green line is known as the MUF, that's the maximum usable frequency. Typically, if you try to use a frequency above the MUF frequency, the frequency is too high and it'll shoot right through the ionosphere, and it won't reflect or refract enough to bounce back and be received on the Earth's surface. So any frequency that is above that green line, typically you do not want to use it since it will not be reflected back down to the Earth. Second blue line is the frequency of optimum transmission. So based on the ITU-533 methodology, the blue line represents what should theoretically, per calculations, be the frequency to be used for communications during that time of the day. So as you can see, between these two stations, there's only a very small area that's filled in with a signal-to-noise ratio of above 10 dB. So below 10 dB, it might be able to communicate, but it might not achieve the data rate that we're looking for. So if we read this chart, what we're looking at is roughly between, let's say, 1,800 hours and 2,200 hours. If we use the upper range of the HF frequency range, so let's say 27 to 30 megahertz, we should be able to communicate with a signal-to-noise ratio greater than 10 dB. So this is with a very low sunspot number. So we're going to rerun this chart, and we're going to have a look at what a higher sunspot number does to performance of this point-to-point circuit. So I'm going to close this for now. I'm going back here to the network screen. Going to click on that point-to-point chart function one more time. But this time, I'm going to artificially increase the sunspot number. So before it was 2, let's say now that the sunspot number is 100. So you can either use the predicted values from NOAA or IPS, or you can enter in your own value. I'm going to click on chart, and you can see now that we're looking at a completely different chart. So with that increased sun activity, with the increased ionization in the ionosphere, you can see that now it's predicted that communication between these two stations, point-to-point communication, should be achievable for over half the day, let's say 2/3 of the day. So from 0 hours to about 800 hours, and we're looking at some points that even have signal-to-noise ratios of almost 30 dB. And then from roughly 1,700 hours to 2,400 hours, again, we're seeing better performance. So not only do these areas filled in color, so your signal-to-noise ratios on the map increase, but what also changes is those green and blue lines, so the maximum usable frequency and the frequency of optimum transmission. So this circuit chart, this point-to-point circuit chart, it shows you the effective sunspot numbers. If you run it for different months out of the year, you will also see some smaller variations, not as large as with the sunspot number, and it also shows you variation during the time of day. So why you'll have variation during the time of the day is typically has to do with during daylight hours. There's not only increased solar activity, but also increased man-made noise. People are out driving cars, machinery is operating. So typically the man-made noise environment is seeing more noise being created. So it's more difficult to create a signal strong enough to combat that noise. So that is a look at the point-to-point chart. And we're going to move on now and have a look at what an actual coverage on the map looks like. So anytime you're creating a coverage in SpectraMe, for those that are familiar, it's typically a two-step process. You create a path loss matrix in the background, which takes into account the propagation method that you're using and kind of creates this file from which you can then create views on the map. So for HF calculations, those typically tend to run a little longer, since in most cases you're running the calculation for each hour of the day, so 24 worldwide coverages. And then if you're using, multiple frequencies, so in this case, most of these stations have 4 frequencies, that's nearly 100 worldwide coverages. So if I was to start that prediction process now, it would take 5 or 6 minutes, but in a 45-minute long webinar, we don't necessarily have the luxury of that amount of time. So the path loss matrices have been pre-run, and now I'm going to show you how to take those path loss matrices that are already existing and turn them into a prediction that can be viewed on the map. So first things first, I'm going to grab this station here, which is just the one station, the Holland 4 megahertz station. Unlike the others, it only has one frequency, and there are 2 options. Now I get to choose whether this station is it's the fixed station that's transmitting, so if this fixed station is transmitting to mobile stations, or if mobile stations will be transmitting to this fixed station. So let's assume this is a fixed station transmitting to mobile stations. Going to click on that function. I have the option of naming this study. I'll just call it the 4 megahertz study. I can choose the year, month, and hour. So again, these will vary the ionosphere conditions and change the way the coverage looks. And since this is a fixed to mobile coverage, I need to select or input the noise environment at the receiver. So several options here for industrial, residential, rural, quiet rural, ships, and rotary wing aircraft. So let's say I'm trying to communicate with receivers that are in rural environments, so I'll choose that there. And for the sunspot number, again, it could be manually input or choose one of the predicted values. So for this month, NOAA predicts 9.5 sunspot numbers. I'm going to allow that to process. That should be fairly quick. And so this is actually the coverage that's being generated. And while this is happening, just a quick word about the propagation models. So SpectrumE uses the ITU recommendation propagation model 533, which is titled the method for the prediction of the performance of HF circuits. So this is the methodology that is used in SpectrumE. And some of you might be familiar with other HF propagation calculation methodologies, such as IonCap or VOACap or IcePack. So those names there, those were created by the Institute for Telecommunication Standards and the National Telecommunications and Information Administration in the United States. And these are all calculation engines that can be downloaded online and are free for public use. And they're all based on empirical models that have been where the data collection started as early as the late 1950s and 1960s. So over time, these have been improved, and kind of the ITU take on this empirical data is propagation model 533, which is used for skywave coverage. So now we can create signal to noise composite coverage for the world for this station and its existing path loss matrix. Again, have the option of choosing a name for this prediction. I'll choose 4 megahertz, and this is a downlink. Going to allow that to process, and now can move to the map.
Martin.
To view. Yes, Sarah?
Just a very quick clarification needed. What do you mean by mobile TX in HF?
So this depends on if the station that you're creating the coverage for. So typically there's one station that's fixed, another one that's a mobile that's moving around. So if the transmitting station is the fixed station and your receiver station is a mobile and can be anywhere, you run the fixed to mobile coverage. and the man-made noise environment is that of that mobile station. And conversely, if you're trying to communicate from a mobile station, so an aircraft, a ship, something like that, you're communicating from the mobile to the fixed. So the noise environment at the fixed station is the one that's going to be used. So it depends on, it's kind of a talk in, talk out, depending on what direction the communications are going in.
Okay, thank you, Martin. I hope that answered your questions, Abraham. Thanks, Martin. You can continue.
No problem. So now we're viewing the signal to noise ratio coverage on the map, and we can see the Holland station here. And on the left-hand side, there is a color palette which tells us a little bit about the signal to noise ratio values. So we're looking anywhere from 10 to 50 dB. And this palette can be edited, it can be stepwise, you can change the minimum and maximum values that appear. For now, we'll just stick with 10 to 50, but then you'll also see these plus and minus buttons. So as mentioned previously, HF coverage varies during the course of the day, and every hour you can expect slightly different performance. So based on universal time, at being the UT there, you can vary. You can skip through the hours of the day to see what your coverage is going to look like. And so all 24 hours of the day will be seen, and typically midway through day when there's a lot of solar activity, your communications might not be so great. But then during nighttime hours, you might see coverage that's many times, sometimes even exponentially larger than it is during the daytime hours. And something else to take note of, you might be curious, why is there no communications directly around the station here? And also at some hours of the day, let's see if we can find a good hour where this is happening. So for example here, again, you have this area of very low signal to noise ratio. And beyond that, you have fairly good signal to noise ratio. So this has to do specifically with the types of antennas that are used in HF communications. They typically have one or more nulls in their vertical patterns. They tend to be omnidirectional in the horizontal pattern, but for vertical pattern, they tend to have one or more nulls. And it is at these nulls when the signal reflects and refracts from the Earth's ionosphere that when the energy comes back down to the Earth, at those nulls, you will have very weak signal to noise ratio. So many times that happens also pretty strongly around the station itself. And again, the performance, their overall performance has to do with the sunspot number and the time of the day, but also the antenna pattern of that antenna. So this was a look at one station. I'm gonna jump back to the network now and gonna grab all the stations except for that one station that's just at 4 megahertz, and gonna create a composite coverage which is gonna take into account the signal to noise ratios from all of these stations. So again, Skywave composite signal to noise ratio. I'll name this entire network. And again, this is a downlink coverage. So I'm looking for the coverage offered by these fixed stations to mobiles, wherever they might be on the world. Going to allow that to process. Go back to the map now. And you will see that now there is a global coverage using the highest signal to noise ratio at any point in the world from any of these stations at one of the 4 frequencies. And as before, as with that one station, you have the ability to scroll through the 24 hours of the day and see the signal to noise variation. So especially here in the Pacific Ocean, we're seeing quite strong signal to noise ratio, sometimes as high as 50 decibels. And actually, I believe this Alaska station here is the only one that has a directional antenna. So you can see to its east, there is an area of fairly high signal to noise ratios. The other stations in this network have omnidirectional antennas. And for example, again, here at Guam, also around this California station, you're seeing that, again, those skip zones. So there are those rings of high signal-to-noise ratios, and between them, those areas where there are the nulls in the antenna pattern. So you're seeing either no good signal or quite low performance.
Martin.
Yes.
Just a clarification question. Does the global coverage take into account interference between stations?
So it does not. This is purely taking the highest signal strength value at a point on the map for any of the stations, not accounting for interference between those signals. And that highest power received at that point on the map is the one that's taken into account and compared against the man-made noise at that point on the map to arrive at a signal-to-noise ratio.
Okay, thank you for that, Martin. Just one other quick clarification. In the coverage chart, the high SNR was shown as blue. What does the red color represent?
So this here we're looking at between 10 and 50 dB, and actually this color palette, it can be changed. Let's see if I have one that I can use. Here we go. So the color palette can be edited by the user. So for example, this is one I had created previously, where depending on what your signal to noise ratio is, it might be equivalent to a certain bit rate. So what I did here is, for example, this blue color is equivalent to 10 dB signal to noise ratio. The green is 20, going to this yellowish orange color, that's 30, and then finally red is 40 dB. So if we equate each of those to a kind of a bit rate for the communications, the user can also create a custom palette like this with 10 or even more levels that they would like. And as you cycle through the hours of the day, you will again see at what points on the map you will have what sort of data rate possible. So there is, there are these abilities to change the color palettes to get the kind of view that the user would like.
Thank you for that, Martin. I hope that clarified the question.
Okay, and one last thing we're going to have a look at before handing over to Ross for ground wave coverage, and that is creating a percent of the day coverage. So we're going to jump back to the network screen here, select the 6 main stations that have the 4 frequencies, and instead of using the composite signal to noise ratio function, I'm going to focus on the composite percentage. Click on that, again, have the ability to name the prediction that is created, and then set a minimum or required signal to noise ratio. So any signal to noise ratio that is below this value is not going to be included in the calculation. So let's set it a little higher this time. Let's say 25 signal to noise, 25 dB. Again, this is going to be downlink. Going to allow that to process, and now going to the map. So this coverage here, this is different than what we were looking at before, where we were able to cycle through the 24 hours of the day. In this case, all 24-hour coverages, so all 24 coverages are taken at once. They're analyzed if at a point on the map, the signal to noise ratio is at or above the minimum required value. And then it sums up those during the 24 hours, how many are above that value, and it creates a percent of the day that you can communicate at or above 25 dB. So for example here, in these red areas, 90 or higher % of the day, so that means that 22, maybe even 23, and more like 21, 22 hours of the day, you will be able to communicate at 25 dB or higher signal to noise ratio. But then once you start dropping, into these green areas, that's going to be somewhere in the 70th percentile. So maybe only 18, 19 hours of the day. And once you're looking at the fringes here at these purple and blue areas, only maybe 50% of the day. So we're talking about, 12 hours of the day, you'd be able to communicate at 25 dB SNR or higher. So that is everything from me. So now we're going to be handing it off to Ross for Groundwave. But before we do that, Sarah, are there any more questions, or are we moving on to Groundwave?
Okay, we do have one question. There are some other questions that we'll pick up at the end. So about the coverage of service in HF, the question is, what about coordination between countries? Do we have to coordinate between other countries whether or not to use the same frequency, or just notify the ITU?
So that's going to depend on the type of HF service that is being used, since depending on the type, whether it is military or naval or a different type of communication system, I believe the rules and the frequency, the spectrum charts, and so on for different regions in the world, and the types of services that are used are going to vary. They also vary sometimes between different nations. So I would say, unfortunately, there's no one set answer for that. Typically, yes, there will have to be some sort of communication, coordination between national standards, international standards bodies, and nations themselves. But again, it's going to be a case-by-case basis.
Okay, and just one further one before we hand over to Ross. Can you change the percentage range so that you can see areas where it can operate for small percentages of time? So that's see areas where it can operate for small percentages of time.
Yes, that is not a problem here. So I'm just going to jump into the palette update. So now I've updated to 10 to 90%. So that gives an area of even these less, I guess you can say, less reliable areas of coverage. So that is possible, and the percent palette can also be chopped up into smaller levels, you can say. So if you want to see it for every 10 percentage points, a certain color, that is possible as well.
That's lovely. Thanks, Martin. I'm going to hand over now to Ross.
Yep, thanks very much. So what I'll be covering for the last section of the webinar today is the groundwave propagation. So within Spectrum E, we're using the propagation model from the ITU P.533, and it's on its 9th revision. So within that, we're going to look at these three stations here, and we'll look at the coverage that we'd expect to see from them as well. So we've got our three stations. So again, these can be selected. What we'll do initially is we'll run this path loss matrix for them all. So if we just select the stations, we can click on this. We'll look at a calculation distance of, say, 400 kilometers, just to go as far out as we need to for this one, just so we're not cutting anything off. So first of all, what we can do looking at the ground wave field strength received. So we've got our ground wave downlink field strength received calculation analysis here. So if we just click that, it'll ask us to name the objects. I think this was Venus, field strength received. And again, we have the opportunity to apply it to the object that was selected when we came into this menu, or for all objects if we want to see a composite coverage for everything. So at this stage, we'll just process this, and then we can see on the map our expected coverage, our expected ground wave coverage for the station here. So the ground wave, the propagation model, it uses curves based on the data up to 30 megahertz, and generally the ground wave will be used when the ionospheric reflections are not the strongest part of the propagation. So here we can see we've got our coverage from our station here. What we can do is we can now do just a composite coverage to see the again using the same tool. Just for all our stations. So this is shown as the field strength received, and as Martin was showing earlier, we can change the palette. to have discrete values, maybe after a certain cutoff, or matching it up with a bit rate for the technology, for the equipment that we're using as well here. So now we can see that we've the coverage, the composite coverage from all three stations is covering this sort of valley area that we're interested in coverage for. So what we now might be interested in seeing is what's the strongest station, what's the best serving station as well. So we're able to do that using our downlink overlap function. So here we can have a look at the individual station coverages to a set level. So if we click downlink overlap, we'll say our thresholds, yeah, 40 dBu. So this is overlap for all the stations. We'll process this, and then we'll be able to see the individual coverages from all the stations. So now we can see the individual stations. What we're going to look at here is identify at what areas how many stations are covering each point on the map. So this is what I've referred to earlier was the best server, which is not what I'm showing today. It's the amount of overlap between stations and how many stations overlap in a specific area. So that's what this is shown as here. So we can see that this Venus station has this orange coverage that overlaps into this Mars area. But sometimes it's a bit clearer when we can just see a count of the number of stations that are overlapping on a specific point. And our next function, again, select the three stations, will be the downlink overlap count. We'll look at a slightly lower threshold here. So say we'll say 25 dBu, and then overlap count. Oh, run that, and then as we go to our map now, we'll be able to see how many sites for each point on the map are serving a certain area. So at our threshold, we can see that all three sites here have a coverage within this green area. We'll have two serving sites on the yellow area, and then the red areas on our map, we only have one site that's providing coverage to that area. So that's a couple of the analysis that we can do with the ground wave. So I was able to show the individual field strength, and again we have the similar function for power received. Then I showed the downlink overlap, and then finally we looked at the downlink overlap count, showing the number of stations that are able to have coverage at a set threshold for the individual points on the map. So I realise we're pushed on time, so what we'll do is maybe open up the floor to questions and answers.
Thank you, Ross.
Thanks for your time today.
Okay, so we have had some questions coming in, so I'm going to fire off. These are specifically relating to that last piece that you were demonstrating, Ross. Can the Skywave assess any grey line effects around twilight? So that the Skywave assess any grey line effects around twilight.
Since that's regarded to Skywave, that currently is not implemented, so not at the moment.
Okay, lovely. Thanks for that clarification. Groundwave. Can you combine Groundwave and Skywave coverages?
I'm not aware that that's possible at the moment. I don't know if Martin, you can input anything further.
As we like to say, anything is possible in software. It might not exist yet, but something like that definitely is possible.
That's lovely. Thanks a lot. Okay, we use the slope method for ground conductivity maps in Iran. Presentations to the ITU-R 3L working party in 2012 is more accurate. I'm unsure quite what the question is there. We'll skip over that one. Sorry, guys, because I have quite a few questions that have come in. Okay, does the software interopolate between antenna patterns for intermediate frequencies. So that the software interoperation between antenna patterns for intermediate frequencies.
It does. So there's different ways of obtaining antenna patterns, especially HF antenna patterns in Spectrum E. The first one is to obtain the antenna pattern directly from the manufacturer. So they will have the greatest amount of information, the most precise patterns, and they will be defined for, sometimes it might be for every megahertz, every 1 megahertz of the HF frequency range. But if you don't have that information, let's say you have information for the antenna at 3, 10, 15, 20, 25 megahertz, but you don't have the values in between, yes, Spectrum E, when you're loading that as a CSV file, it will take the information that you have for both the horizontal and vertical patterns, and it will not only interpolate, the pattern itself. So let's say you have the pattern defined every 10 degrees. It'll create a full, 360 degree or 180 degree pattern out of it. But then for the missing frequencies between those intermediate frequencies, it can interpolate those values, and there will be an antenna pattern present, even though you don't have, necessarily that frequency, the antenna pattern for that frequency defined.
That's lovely. Thanks for that, Martin. We do have another question here. Within the galactic and atmospheric noise, Spectrum E appears to use medium noise values. Is it possible to have skywave calculated based on the 90% values? Equations for the ITU-533. This is not referring to the availability or the percentage of time.
So this has, as I mentioned before, anything really is possible on software. A lot of times it depends on, do we want to be asking the users all these potential questions? Some users might, just want a fairly quick calculation without needing to go into the nitty-gritty. So based on the user, we do have the ability to add further functionality to be able to take further variables, further values into account. So again, it is a software. So currently that is not open to users of Spectrum E. But if there is a great need for that, of course, our developers are always looking forward to looking for new functionality to be added. So that is to say, currently, at the moment, for that to be a user editable feature for 533, it is not. But if there is a need for it, it is possible to add such functionality to Spectrum E.
Okay, lovely, thank you. Hope that helps, Michael. Is it possible to export the 24-hour Skywave coverage to Google Earth?
That's a good question. I'm not even sure myself if it is. So again, that's more of a software and implementation question. I would imagine that it should be possible. So as far as I'm aware, I don't believe that functionality exists yet. But again, it should be something that's possible to implement.
That's lovely. Thank you for that, Martin. For Groundwave, is it necessary to have a DTM layer?
So as I understand, we have the terrain maps within Spectrum E, and I believe that they're utilised in the groundwave propagation as well. So obviously, to get more accurate results, the more information that you can put in that's relevant to the propagation analysis that you're doing. So we saw a bit of shielding on the example up that sort of valley within the project.
Super, thanks for that, Ross. Is this sort of communication, I'm assuming you mean referring to HF, functional for submarine links?
So if the submarines, if they do use these frequencies for communication, then yes, it can be used for that. Although the performance of the links, et cetera, is going to be highly dependent on the type of system that is used, what sort of signal powers and signal to noise ratios are required for the system to be functional and for successful signal reception.
That's lovely, thanks for that. Just going to go back to a question we had earlier, which was about coverage service in HF and coordination between countries. And I know you did mention that it was relevant to which frequencies you were using. The frequencies our user was referring to was radio AM coordination, the 550 kilohertz to the 1600 kilohertz band. Does that make any difference to that?
So with regard to that, when it comes to the AM broadcasting, there are some differences to that, and I can't necessarily comment exactly on any kind of rules or procedures to be used for AM broadcast. And again, AM is AM per se can be similar to HF, but it can also be different. So again, it's just going to depend on the ITU and the national level specifics with regards to that specific frequency band, that specific type of service, whether it's on a primary level, secondary basis, and so on. So off the cuff like this, it's a little hard to comment, but there is plenty of variation in the rules of play.
Okay, that's lovely. Just to clarify something that Ross just covered about the DTM, the terrain data is not used in the 368 calculation. Ground wave propagation is limited to the conductivity and permittivity data related to the terrain, but not to the elevation points. So that's just to clarify a question that we had earlier. Okay, just moving on to the next question. Okay, so we have another one here regarding sunspots. Where exactly is the sunspot data from, and is it possible to predict sunspot numbers in the future? Martin.
So with regards to the sunspots, the two main sources for those are as you see in the tool itself, you have the ability to choose information from NOAA, from the NGDC, the National Geophysical Data Center, or from the Australian government's Bureau of Meteorology, the Space Weather Services. So sunspot data has been collected for the past, let's say, 250 years or so, and during this time of collection, it's been seen that there's roughly, there's a periodicity to sunspot numbers, to the monthly mean sunspot numbers. And it's roughly an 11-year cycle. So based on this data, NOAA and the Bureau of Meteorology in Australia, they use kind of the sinusoidal nature and long-term trends, and they try to predict the values at least 2 years into the future. And then, every month as sunspots are recorded, the two services will update their predictions for the next 2 years. Typically, it's a little harder to go for more than 2 years, but at least for the upcoming 2 years, based on this historic data, the cyclical nature of sunspots, and just long-term trends, the predictions are made.
That's lovely. Thanks for that, Martin. We have 2 more questions, so thanks, guys, for your patience. I do appreciate that. We have overrun just by a few minutes. How do you determine or calculate the receiver noise level?
So the receiver noise level is typically, there's variation in it. It really depends on what sort of environment that the receiver is going to be in. In many cases, there are ITU recommendations and even ITU software for it. So one such recommendation is M1467, which mainly has to deal with some naval applications. There's a software package from the ITU called NoiseDat, which also helps a user determine what sort of man-made noise levels to use. And sometimes man-made noise can kind of be similar to clutter height and clutter loss settings in the RF world, as in there might not necessarily be one set standard to use. There will be a little more variation to it. but the ITU does have some recommendations of what values to use for the man-made environmental noise.
That's great. Thanks for that, Martin. Just one last question about calculation speeds. How long did the demo network take to calculate for the worldwide coverage? So that was that worldwide coverage you did earlier.
That's a good question. So when it comes to those coverages, you in that example network, there were 6 stations. Each of those stations had 4 different frequencies. And we're calculating, for 24 hours during the course of the day. So, that's several hundred worldwide calculations that need to happen for that, for that ultimate total coverage to be shown. So the calculation speed, so for those 6 stations, the 4 frequencies, 24 hours a day, it didn't take any more than 10 minutes. Again, that would have been too long to show during this webinar, but it really didn't take more than 10 minutes. And some older software might take hours and days to calculate that. So what we do, we use the fact that Spectrum-E, there's several different implementations of it. It can be installed on a local host in a PC. It can be installed on a LAN network. It can be installed in the cloud. So in our cloud service, we have processors with many cores, and we support distributed calculations so that we can vary the computations and distribute it across several CPUs, across several computers, allowing it to run faster. So it did take less than 10 minutes to calculate all of those.
That's lovely. Thanks for that, Martin. Just to clarify, all of the demonstrations that have taken place today have been in Spectrum-E. The HF module is available in that. Okay, we do have a couple of other questions. What I would suggest we'll do is we've got more coming in. We'll hang on. I've got just a couple of housekeeping things to follow through for anyone that is likely to drop off. I will be sending you a survey link at the end of today's event. I please urge you to complete that. It takes 3 minutes of your time. It enables us to understand how you felt about today's survey, and it also builds future surveys, subjects for future surveys. I'll be sending you the handouts from today's events and an invitation to our next webinar by email later, along with a link for today's recording. Please feel free to share that link with any colleagues that were not able to attend. Okay, so we're just going to quickly go back to the questions. This one is, can the HF module export or recommend frequencies for coordinating between countries?
So, so that would be kind of a frequency nomination function. And ultimately, something like that would be possible, but it would be necessary to, one of several things would be necessary. It would be necessary to know all the stations around the world, or at least around the area of interest, that are already operating. So you kind of have to create your incumbent stations to compare against. So it'd be necessary to use that, and then also import a channel plan for the actual usable frequencies, again, depending on if that's on a national level or an international level. And Spectrum-E does have functionality. It's not hasn't necessarily been linked to HF yet, but it is, these sorts of interference-based frequency selection functions already exist in Spectrum-E. So, kind of carrying that over to HF would also be possible.
Thank you, Martin. Is it advisable to establish coverage for an AM dealer, considering both Skywave and Groundwave can vary the map of the station's operating coverage?
So I see we're getting more into the AM related questions. So I think we might need to have a another webinar specifically on AM FM communications, since today we were kind of covering HF purely in more of an RF matter, and when you get into AM FM, you start getting more into regulations and things like that. And we do have fairly extensive AM FM functionality in Spectrum-E, so we might have to make a note of this, and one of our future webinars should probably focus on AM and FM specifically.
That's lovely. I hope that answers your questions, Marlon. You will receive any updates in terms of future webinars by email. So any invitations that we do on that will come to you directly. Just a very last one, near vertical incidence skywave. So this is, can you have a little bit of more information about near vehicle incidence skywave propagation and what the possibilities of calculations, whether it's feasible in spectrometry at the moment?
So from my understanding of near vertical incidence skywave, a lot of times that has to do with the type of antenna that is used. So I know there are certain types of HF antennas that are specifically meant for the near vertical incidence skywave. So these NVIS antennas, it is definitely possible to import them and use them in spectrometry and use them to generate coverages. But if it goes beyond that, and there's other special characteristics of NVIS that would require further implementation, that's something we would likely have to take offline and discuss more specifically the functionalities that are being sought.
That's lovely. Thank you for that. Thank you, everyone, for your questions. And thank you. I'd just like to take this opportunity to say thank you to our presenter, Martin Reyes and Ross Davison. We have a webinar, our last one of this year, will be held on Thursday, the 5th of December. We'll be covering ITU-R propagation model 452, its implementation in spectrometry. You'll be receiving an invitation for that after today's event. Thank you, everyone, for joining with us. Thanks for your patience. We have gone a little over time. You'll be hearing from us shortly.